So this week we're learning about entropy and Gibbs free energy, and our learning intentions are to analyse the differences between entropy and enthalpy, to use modelling to illustrate entropy changes in reactions, and to predict entropy changes from balanced chemical reactions to classify as increasing or decreasing entropy. So Gibbs free energy we'll touch on later in the week, but as way of an introduction to entropy, consider that there are almost limitless numbers of chemical reactions that can be performed. There are countless compounds and chemicals we can put together, but could we predict whether a proposed but as yet untried reaction was possible? So let's just say we're in the lab, no observable reaction occurs between a set of chemicals we're putting together. Does that mean that the reaction is very slow under the conditions used and may become faster under more suitable conditions, say an increase in temperature? Or does it mean that the reaction will not occur under any conditions? Now, we can save ourselves a whole heap of trial and error and a lot of time if we can use a formula to calculate whether the reaction will not occur under any conditions, or we can actually calculate whether the reaction may occur. And that's what we're going to work towards this week. We're going to attempt to answer the question of whether a reaction is spontaneous or not. And when we say spontaneous, we mean that it doesn't require any outside energy to get started. Systems always tend towards a state of lower energy. Exothermic reaction, you can see here, diagram B, we have a system moving towards a state of lower energy. This would obviously be a negative delta H value, being exothermic. But some endothermic reactions occur spontaneously, and you can see here we have actually a move towards a higher state of energy. Liquids such as ethanol evaporating, obviously we've got a delta H plus value. So again, it's moving away from that general trend of moving towards a state of lower energy. So there must be something else happening here that moves these endothermic reactions away from that general trend of lower energy. There must be some other natural tendency in addition to the drive towards lower energy. And we find that in nature, in addition to a drive towards lower energy, which you can see here, they're exothermic, there's a drive towards an increase in chaos, or an increase in randomness, we might say. That is basically what entropy is, an increase in randomness. So there are two basic drives when it comes to thinking about chemical reactions, and the first one we're familiar with, enthalpy, capital H, a measure of the total energy possessed by a substance or group of substances. And as we've already just seen, in nature, substances or systems tend to move from a state of high energy to a low energy state, just like in an exothermic reaction where your products have a lower energy level or lower enthalpy than the reactants. The other drive we're going to start thinking about now is what we call entropy, capital S, and that's a measure of the randomness or disorder or the chaos of a substance or of a system. So you can see this little animation down here. This is Brian Cox. It's a really good documentary. Recommend you might want to go and have a look at this. He talks about entropy and the fate of the universe, the fact that the entire universe is moving towards a state of chaos and disorder. So the example he used here is a sandcastle. You build a sandcastle made out of millions of grains of sand. There are very few ways those sand particles can be arranged in order to create a sandcastle. However, there's an infinite number of ways that those sand particles can be arranged that don't resemble a sandcastle and resemble a pile of sand. So things tend towards high entropy or high levels of chaos because there are far more ways of arranging substances or particles or molecules randomly than there are with high order. And you'll have to put energy in, like he actually had to build that sandcastle. So you've got to put energy in order to create low entropy. So everything tends towards high entropy. Over here as well is another example. You can see the ordered structure of a glacier. But it's always disintegrating into chaos, into smaller particles with random orientations and movements. You'll never see a chunk of ice leave the water and reattach itself to a glacier. It could happen in theory, but it's highly unlikely. So everything in nature tends towards chaos. Have a look around the room you're in right now. If you haven't cleaned it up in a while, if you haven't put energy in to create order or low entropy, I guarantee you it's probably messy. Everything tends towards disorder and chaos unless you put in energy to get that entropy down and create some sort of order. Another example up here, this is from your textbook. You have a jar of Smarties, you mix them all up. They are not going to spontaneously create order from that chaos. You need to put energy in order to get all of those Smarties back in their respective colors. So in chemical reactions, the drive towards minimum energy usually dominates, which means exothermic reactions are much more common than endothermic reactions. There are some reactions though where the drive towards maximum randomness, which means higher entropy. Remember, entropy is randomness and chaos. That drive towards higher entropy is stronger than the energy drive, and this means that sometimes endothermic reactions can be spontaneous, or they don't need external energy to get started. So we've got two processes occurring down here. Both of them have a positive delta H, so they're both endothermic reactions. They occur as written because the drive towards increased entropy or increased randomness is stronger than the drive towards lower energy. Therefore, you are going to have an endothermic reaction with the drive towards higher entropy overcoming that drive towards lower energy, which is what would happen if we reverse that and it was an exothermic reaction. So a move from an ordered state to a less ordered one, so from ordered to less ordered, corresponds to an increase in entropy, meaning delta S, or change in entropy, is positive. The drive towards greater entropy or greater chaos or randomness is greater in that case than the drive towards lower energy. So the reactions occur in the directions written, which is what we've just gone through here. This drive towards higher entropy from left to right through this equation is stronger than the drive towards lower energy from right to left if we reverse this and it was an exothermic reaction. And the same applies for this down here for our evaporation of ethanol. From a liquid to a gas, we have a drive towards higher entropy, and these reactions are as written because that drive towards higher entropy is greater than the drive towards lower energy. So before we get into any of the quantitative calculations of entropy and Gibbs free energy, let's just look at estimates or qualitative estimates of randomness and entropy. So the first one we want to note down here is entropy increases as the substance changes from a solid to a liquid to a gas. If you have a look at these diagrams down the bottom here, solid, liquid, and a gas. And as we move from left to right along here, excuse me, entropy increases. In a solid, particles are arranged in a very specific manner. They're vibrating back and forth, but there's a fair bit of order to it if it's a solid. Once you get to the liquid state, the particles are moving around a little bit more, and compared to a solid, there's a little bit more randomness and chaos in the motion of the particles, so the entropy has increased. By the time you get to a gas, it has more entropy, it has more randomness than the liquid or the solid. Particles are moving around very quickly. They have many different orientations, therefore a high amount of randomness and a high entropy. So gases here at very high entropy. Okay, different solids have different values for their entropies per mole, which we can look up. But these differences are quite small when compared to the differences between the entropies of a solid and a liquid, or if you were comparing a liquid to a gas. And when a solid dissolves in a solvent, there's an increase in entropy when a solid dissolves. This all goes back to this idea here of the levels of randomness and chaos in a solid, liquid, and a gas. Think about the particles and their motion. So to estimate qualitatively the change in entropy for a chemical reaction, which we're going to do in a second, consider the following. Have a look at whether there's a change in the number of moles of solid, liquid or gas in the reaction, or you can have a look at whether a solid has been converted to a solution. Here's a couple of examples so we can have a look qualitatively, just having a look at some reactions and getting a feel for the randomness or entropy in these particular reactions. So we have a look at chlorine gas to liquid chlorine. Entropy is decreasing, and what we're looking at here is we're going from a gas to a liquid. Number of moles have stayed the same, but we're going from a substance or a state, gas, high amounts of entropy, to a liquid. We're moving back down towards a solid, so we have actually decreased the entropy in that particular reaction. Now if we have a look here, we're going from a solid, calcium carbonate, and we've got another solid forming, and we're actually forming a gas as well, so we have increasing entropy. Entropy is increasing because we're producing a gas which has high entropy from a solid, and also the number of molecules is increasing as well, so we've gone from 1 on our reactants to 2 molecules over here in our products. Let's have a look at the last one we've got here. We've got nitrogen, we've got a gas, and we've got a gas, but we have, what have we got? 4 moles on this side, and we have 2 moles of gas on the right, so we have a decrease in entropy because 4 total reactant molecules are forming 2 total product molecules, and all are gases, so the state of those substances doesn't really come into play in this particular example. We're just looking at number of moles or molecules being formed. Okay, let's have a look at our ethanol. It's ethanol evaporating here, and it's an endothermic reaction, so we have an increase in that energy level, we have an increase in enthalpy. So 1 mole of liquid ethanol has been converted to 1 mole of gas. This corresponds to a great increase in randomness and is so an increase in entropy. The fact that we're going from a liquid to a gas, liquid to a gas, entropy has increased. So the drive towards increased randomness, or the drive towards entropy, is large and strong enough to overcome the energy drive, which is in the opposite direction. Hence the process goes as written. Delta S, change in entropy, would be positive, and we can see going from a liquid to a gas, we have increased entropy. This reaction is as written, and it's overcome the drive to the left of energy. So remember, if we reverse this, would have an exothermic reaction. So this drive towards entropy chaos is overcoming that drive towards a lower energy state, which would happen if it was an exothermic reaction. This is the same idea here, as we've got an endothermic reaction, decomposition of calcium carbonate at 1500 Kelvin. We have an increase in the energy level, and remember, usually things would tend towards a higher to a lower energy state. We have 1 mole of solid converted into 1 mole solid plus 1 mole of gas, so we've got our CO2 gas here. So we're going from a solid and we're producing a gas. So again, we've gone from solid here and produced a gas. So our entropy is increased, the randomness and disorder. This equation or this reaction occurs as written from left to right. So that increase in entropy must be greater, or that drive towards higher entropy is greater than the drive towards lower energy. So this would be lower energy. Again, reverse it. We have an exothermic driving towards lower energy, but in this case here, this drive towards higher entropy must be stronger in this case. And again, delta S, change in entropy, is positive. So we can use this table here. This is table 16.1 from your textbook. We can use this to help us work out which drive is larger when we're talking about some of these reactions. So if we look at our calcium carbonate here, our reaction, it's the same one we've just been looking at, and we know we're going from a solid to a gas, so the entropy drive is forward, increasing entropy in the forward direction. We know this is endothermic, so the drive to lower energy would be backward. So this is the energy drive, and the bottom one here is our entropy drive. Alright, so let's look at this table and see if we can work out which is larger. We've got the energy drive is for backward. Energy drive is backward. The entropy drive is forward. The reaction go as written? Yes, it does, from left to right. Therefore, the entropy drive is larger. So here's a worked example we'll go through, and then I'll get you guys to do one on the next slide. So the question 1 here is predict with justification whether the changes in entropy for the following reactions are positive or negative. So we can see here our reactants are a solid and a gas, and we're producing a solid. So in that case, we are actually decreasing our entropy. So entropy here would be negative. Because we're going from a gas to a solid, we have decreased entropy. Therefore, the entropy change is negative. Now, when you talk about your justification, I'll let you have a read through this paragraph here and you can see what we're talking about. But again, we're just looking at these states here and determining whether entropy is increased or decreased. If it's increased, change in S is positive. If it's decreased, change in S or change in entropy is negative. Let's have a look at our next one here. We're going from a solid to 5 moles of gas. So massive increase in entropy there. So we would have a positive and very large change in entropy, and I'll get you again to have a read through that if you like about how you would justify your choice there. Okay, so question 2, both these reactions go in the direction shown. Okay, good to know. The reaction in part A is exothermic, while in part B it's endothermic. So this one up here is exo, and this reaction is endothermic. Deduce the relative magnitudes of the energy and entropy drives in these reactions. So if the top one, let's look at A here, if this is an exo, we would have a energy drive from left to right. So we'd have a reduction in the energy. And we can see we've gone from a gas to a solid. So the entropy drive for this one here, I'm just running out of space, so I'm going to put this arrow above it. For that particular reaction, the entropy drive would be backward. And it's as written. So now we can use our table to work out, or you might be able to work it out by now without using the table, but let's use the table anyway. Yes, it is as written. We have a forward energy drive, and we have a backward. So we can say we've got a forward energy drive, we have a backward entropy drive. It is as written. The energy drive is dominant, is larger. So we can do the same one for the endothermic. So if endothermic, it would mean that the energy drive is backward, because if we reversed it, we'd have an exo. And we're going from a solid to 5 moles of gas. So the entropy drive is in the forward direction. So we would say, yes, it is as written. And we have a backward energy drive, and we have a forward entropy drive. Entropy is the dominant driver there. Again, you might want to have a quick read through the justifications here to see how we arrived at that, if you like. And then what I'll get you to do is move on to the next slide, and we can I'll get you guys to do one of your own. Okay, so here's one I want you guys to try yourself. I'll get you to work on this before our next lesson, and then the first thing our next lesson I'll ask some people in the class to give us their answers and justifications for some of the answers to these questions here. You can use this table from your textbook if you get stuck. Feel free to email me if you need a hand. But apart from that, enjoy, have fun, and I look forward to hearing some of the answers next time I see you guys. Okay, bye.